Hello, this is Choose Socrates, and our video for today is about orthogonal complements. Now, in our last video, we talked about the dot product, and we are going to build on the ideas that we saw in that video. So if you haven't seen it yet, now would be a good time to watch it. In this video, we are going to learn a lot of stuff. So we will see the definition of the orthogonal complement W perp of a subspace W. We will see what W perp looks like in R2 and R3, the spaces that we can see. And we will see how to compute a matrix product using dot products instead of linear combinations of our columns. We will see that there is a relationship between the concept of orthogonal complement and the four fundamental matrix spaces that we saw a couple of videos earlier. And because of this, we will see how to use a matrix to find the basis for the orthogonal complement of subspace W given a spanning set S, where W is the span of S. And also, we will see an analogous theorem for orthogonal complements, a lot like the dimension theorem for our fundamental matrix spaces. And finally, we are going to see the 2-for-1 theorem for bases. So let's start off with that word complement, and there's another word in English that is similar to that, where the E is turned into an I. So we have complement instead of complement. So they both have the same root in Latin, but they mean kind of different things. So in our case, the word complement refers to something that completes something else. So we're going to see how W perp, in a sense, completes W in Rn. The other word complement talks about something nice that you say about another person, let's say. So like you have nice shoes, you have a nice hairdo, that's what you call a compliment. So what is the meaning of an orthogonal complement? If W is a subspace of Rn, then W perp, the orthogonal complement of W, is defined to be the set of all vectors in Rn, V, so that V dot W is 0 for all W in the subspace capital W. And this W perp is also a subspace of Rn. So if you recall, there are three important properties for a subspace. It must contain the 0 vector, it must be closed under vector addition, and closed under scalar multiplication. So let's start with the 0 vector. Why is it that the 0 vector in Rn satisfies the definition in W perp? So we want the 0 vector when dotted with any vector in W to be 0. But that's trivial. The 0 vector dotted with any vector W, in fact any vector W in Rn, is always going to be 0. So therefore it satisfies this equation. Now what about closure? So let's take two vectors now, V and U, from W perp, and because they're in W perp, then their dot product with any W in our subspace capital W must be 0. So how about the vector sum V plus U? Well, we have properties for the dot product. So if you take V plus U and dot it with any W from our subspace capital W, we have the distributive property that becomes V dot W plus U dot W. Well, both of those dot products are 0. So it's kind of like we're back to chapter 0. 0 plus 0 is equal to 0, and so V plus U is also orthogonal to W. And of course, if you have a scalar multiple, say R times V, then this time we have the homogeneity property. R times V dotted with W, you can factor out the R and multiply by the dot product V dot W. We know that V dot W is 0, so R times 0 is 0, which tells us that R times V is orthogonal to W for all W in capital W. All right, so now that we know that W perp is also a subspace, let's take a visit to GeoGebra and find out what this looks like in R2 and R3. Correct. Let's start in R2. So we know that the non-trivial subspaces in R2 are the lines passing through the origin. So let's say we have y equals 3/5 x. So let's write that as 3x over 5. Okay, so there's a line passing through the origin. And, well, we might as well think of a basis for this line. So the slope is 3 over 5. So the vector 5, 3 is on that line. So let's make our vector to 5, comma 3. All right, so there it is. Okay, so that vector is a basis for our line. Now, we want to look for all the vectors which are perpendicular to every vector in this line. Okay, so in particular, it has to be perpendicular to 5, 3. Well, it's not that hard to think of a vector perpendicular to 5, 3. So the dot product has to be 0. Okay, so let's play with those numbers, 5, 3. So if x is 3, then we have 15. We want negative 15. So we multiply 3 by negative 5. There it is. So there is a vector which is perpendicular to that line. Okay. Are there more vectors? Well, of course. Any vector parallel to v, a scalar multiple of v, will be perpendicular to this line as well. Okay. So it looks like we're going to get a second line. A second line passing through the origin, which is perpendicular to our first line, y equals 3x over 5. And I hope you remember our basic algebra. The slope of that line is the negative of the reciprocal of the slope of this line. So the equation is y equals negative 5x over 3, or negative 5/3 x. And there it is. That line contains our second vector and is perpendicular to our first line. Let's think about going backwards. What if you start on this line and you ask, well, who are all the vectors which are perpendicular to that line? Well, it's got to be the vectors on the first line. Okay, so that tells us that our two lines are actually orthogonal complements of each other. So they make a pair of mutually orthogonal subspaces of R2. Okay, so now let's take a look at R3. There it is. Just kidding. All right, let's make a subspace in R3. So there are two choices of non-trivial subspaces. This time we have a line passing through the origin, just like in R2, and we also have planes passing through the origin. Okay, let's start with a line. So a line is the span of a single vector. So let's make a direction vector. Let's say 5, negative 3, 2. Okay, so there is a direction vector for a line. And of course, the line is made of all scalar multiples of this vector. Okay, so we can make, how about negative 2u? Okay, there we go. So that pretty much looks like a line in space already, passing through the origin. Who are all the vectors which are perpendicular to that line? Okay, so we're looking for all the vectors x, y, z in R3, so that when you dot it with 5 minus 3, 2, you'll get 0. Okay, so what happens when you dot x, y, z with 5 minus 3, 2? You get 5x minus 3y plus 2z. And you want to make that equal to 0. Well, that's exactly the equation of a plane, right? The plane 5x minus 3y plus 2z equal to 0. Boom. There it is. So if you look this way, look that way, oh, there it is. The plane has disappeared because it just looks like an edge over there. Let's make it like this. So all the vectors on that plane are perpendicular to our line. Okay? And again, let's play the other game that we did in R2. If you start now with a plane through the origin, if you start with this plane, and you can ask, well, who are all the vectors that are perpendicular to each and every vector on that plane? Well, that has to be the normal line. Okay? So again, subspaces in R3 come in orthogonal complement pairs. The normal line is the orthogonal complement of the plane, and the plane is the orthogonal complement of the normal line. So they are orthogonal complements of each other. So let's summarize what we just saw in GeoGebra and state it in general terms. If you have a line which is a span of AB, a non-zero vector in R2, then its orthogonal complement L perp must be the span of negative B comma A. So remember what we did. We exchanged A and B, and we changed the sign actually of the second component. So what we did was the span of B negative A. And of course, these two vectors, minus BA and B minus A, are just negatives of each other. So they're both valid basis vectors for our line L perp. And similarly, the orthogonal complement of the line, which is the span of ABC in R3, is the plane pi L perp with Cartesian equation AX plus BY plus CZ must be 0. And the orthogonal complement of that plane is the normal line, the span of ABC. So we will see this in general, that at least in Rn, W and W perp are orthogonal complements of each other. They form a pair of orthogonal complements. So our next goal is to generalize our computations in R4, R5, in higher dimensional spaces. We saw what to do in R2 and R3. What do you do in R4 and so on? All right. So if we're given that W is the span of several vectors, W1 through Wk in Rn, then W perp is made of all the vectors V in Rn, so that V dot with each of these vectors is 0 for all I equal to 1 to k. So this is a big improvement over the definition, because instead of having to check that our vector is orthogonal to all the vectors in our subspace, we only have to check it for a spanning set of vectors for our subspace, in particular for a basis. And why is that? Well, any vector in W is a linear combination of these vectors. So if you dot that with V, then we can use the distributive property, and then after that, the homogeneity property. So we will get V dot W1, V dot W2, and so on with coefficients. All of the dot products are 0. You multiply by coefficients. You'll still get 0. Add them all up. You'll get 0. Okay, so let's apply that to this example. We have this subspace W from R4. And it looks like these two vectors, which span W, are not parallel. So they are a basis for W. W is two-dimensional. We want to find a basis for W. So according to this theorem, all we have to check is that the dot product of our vector V in Rn is 0 with both of these vectors. Okay. So if we represent our vector V as V1, V2, V3, V4 as usual, we must have that the dot product of V with the first vector must be 0, and the dot product of V with the second vector must also be 0. But we know that we can distribute this dot product, compute it as 3V1 minus 2V2 plus v3 minus v4 has to be 0, and minus 5v1 plus v2 plus 3v3 minus 10v4, that should be a minus 10v4 must also be 0. Oh, would you look at that? We have a system of equations, big surprise, and the right side is 0. We are solving for v1, v2, v3, v4, so we are looking for all the solutions to this homogeneous system of equations. How do you do that? You make a matrix, and then you look for the null space of that matrix. All right, so here's our matrix: 3 minus 2, 1 minus 1, minus 5, 1, 3, minus 10. And we go. Compute matrices RREF. There is our RREF. So we have 2 leading variables and 2 free variables. Let's practice sight reading our null space. So I hope you remember how to do that. First, we will make a couple of blank vectors. How many are we going to need? The vectors will be from R4, of course, because we have 4 columns. And we need 1, 2 of those blank vectors because there are 2 free variables. Okay, so let's make a couple of 1x4 vectors. Magic, I had them ready for us. Okay, so there they are. And we will put a leading, no, not a leading one. Remember, they're called trailing ones at the columns for the free variables. So we will put a 1 in column 3 and a 1 in column 4. Everything to the right of the trailing one has to be 0. Everything to the bottom, below the trailing one, must also be 0. Okay? So, what goes into the blanks? In column 3, we have minus 1, minus 2. They go into the first vector, reverse the sign as you input them. So we will have 1 and 2. And in the fourth column, we have 3 and 5. Reverse the sign when you enter them. -3, -5. So that is our basis for the null space. And in this case, this is also a basis for our orthogonal complement because we said that we are solving for the solutions to the homogeneous system. And of course, we're going to see that that is going to be true in general. So here is our basis for WPERP. Before we go though, let's check that the dot product of these 2 vectors with our 2 vectors from S really are 0. So we have 3 minus 4 is -1, plus 1, 0, that's 0. How about with the second vector? -9 plus 10 is 1, 0 minus 1 gives us 0. How about the second vector? With the first, we have -5 plus 2 is -3 plus 3, 0. The last term also contributes 0. And finally, we have 15 minus 5 is 10. 0 minus 10 will give us 0. Yes. I almost forgot. There's one more thing I wanted you to notice, and that the 2 rows of the matrix that we assembled are the 2 vectors that we have in our basis S for W. 3 minus 2, 1 minus 1, minus 5, 1, 3, minus 10. And of course, this is going to be the general principle that we're going to use in our later computations. All right, so to see why we can generalize this to any spanning set for a subspace, let's take a look at another way to compute the matrix product. So you have a matrix A here on the left. It is M by N. and we have a column matrix. So we have an n by 1 column matrix. So remember that the number of entries in the column matrix must be the same as the number of columns of A. So we said that the definition is you take column 1 of A over here and you multiply it by x1, the first coefficient. Take column 2, multiply by x2, and then you add all of those together. That's the definition of the matrix product. But take a look at what we're going to get in the top row. You have A11 multiplied by x1. That's right here. A12 multiplied by x2, and so on. A1n multiplied by xn. But they're pairs of numbers multiplied together and then added all up. Isn't that just a dot product? All right, so we can put all the x's together as x1 to xn and dotted with a11, a12 to a1n. But those are exactly the numbers at the top row of the matrix. All right, so the first number that we get is simply the dot product of x with R1. And of course, we have the commutative property for dot products. So that's also R1 dotted with x. So obviously, this idea works on any row. So here's our original matrix A multiplied by x. We can think of A as partitioned into row 1, row 2 through row m. And then we multiply that by x1 to xn. But instead of breaking up x into several components, we just take the dot product. So our top entry is x dot r1 or r1 dot x. Our next entry is r2 dot x or x dotted with r2, and so on. So we call this the dot product formula or perspective for the matrix product. So now we can use what we just did to go back to the 4 fundamental matrix spaces and see that there is a relationship between the row space of our matrix and the null space of our matrix. A vector x from Rn is a solution to Ax is a zero vector if and only if x dotted with every row of our matrix is 0. Okay, why is that? When you multiply A by x, you get the dot product of x with each of the rows, but you want the 0 vector on the right. So you want all of those dot products to be 0. So another way to say that is that x is in the null space of A if and only if x is orthogonal to all the rows of A. The dot product of x with each and every row has to be 0. So if W is the row space of A, then W perp must be the null space of A. And similarly, let's turn it around. If U is the null space of A, then U perp is the row space of A. So in other words, the row space and the null space of our matrix A are orthogonal complements of each other. So we are now ready to generalize what we saw in our last example. If W is the span of S, a set of vectors from Rn, S is W1 through Wk, and we form the matrix B, whose rows are W1 through Wk. Then W is the row space of B, and W perp, the orthogonal complement, is the null space of B. So remember how we solved the homogeneous system? We found a basis for the null space of that matrix. But as a bonus, remember that a basis for W is also the non-zero rows of the REF. So even though we didn't do that for our last example, we're going to do it for our next one. Now, this other theorem is actually exactly the same thing as this theorem, except it's stated in a slightly different way. So we have the same setup, the same first line, as you can see. But instead of forming the matrix B with rows W1 through Wk, we formed the matrix A, which we called the matrix of S, whose columns are W1 through WK, as usual, just like in everything else that we have done. So this time, who is W? It's the column space of this matrix A. All right? But we said before that if you turn rows into columns or columns into rows, what you get is the transpose. So therefore, this matrix A is simply the transpose of B. And similarly, B is the transpose of A. So the column space of A is exactly the same as the row space of A transpose, which is the row space of B. And therefore, based on this last theorem, W perp is the null space of the transpose of A. So this gives us a connection, a purpose for the null space of A transpose. If you assemble a spanning set for W as the columns of a matrix, then the orthogonal complement of that subspace has a basis which we can find using the null space of A transpose. Okay, so let's take a look at an example. Let's put all of this together. All right, our last example was from R4. This one is from R5. So we have W is the span of S, and this time S contains 5 vectors from R5. So it's possible that this is all of R5. We're going to see in our computations. First, we're going to construct the matrix of S as usual, putting these vectors into columns. We're going to apply the minimizing theorem. So this is a good review for a couple of videos back. We'll find the dimension of W. Maybe it's 5, maybe it's smaller than 5. We'll find the transpose of this matrix, and then we'll look for a basis for the orthogonal complement using the null space of A transpose, what we just mentioned. And because of this, we can find the dimension of W perp. We are going to find a second basis for W using the REF for A transpose. So remember, that's just the non-zero rows of the REF. And as a nice icing on the cake, we will express the fourth vector of S as a linear combination of the basis vectors that we find in E. Okay, so I've gone ahead and formed the matrix of S. We have the first vector found in column 1, the second vector found in column 2, and so on. Okay, so let's apply the minimizing theorem. Let us take the REF of this matrix. So we will compute matrices REF. Okay, so there is our RREF. So we have leading variables in columns 1, 2, and 4, and our free variables are in columns 3 and 5. Okay, so the minimizing theorem says that our basis for A is made of the first, second, and fourth vectors in S. So let's just copy that whole thing, and let's put our answer over here. Our basis for W, let's now call it B, is made of the first, the second, and the fourth. So we erase the third vector, and we erase the fifth vector. Okay, so that is our basis for W, and of course the dimension of W is equal to 3. So it's not all of R5. It's only a 3-dimensional subspace of R5. Okay, our next job is to find the transpose. So let's do that over here. Let's just put that on the next line, and then we go compute matrices and transpose. Okay, so we can now see that the rows of this matrix is made of these 5 vectors. Okay, Here's first vector, and that's in row 1. Let's look at the last one. 5, 2 minus 1, 1, 6. 5, 2 minus 1, 1, 6. So the vectors are now written into rows. Okay, so now we are ready to find the null space of the transpose, and that will help us get a basis for the orthogonal complement. Compute matrices REF. Okay, so of course the rank is the same. The rank is 3, and we have 2 free variables. So we're going to sight read the basis for our null space as before. We will need 2 empty vectors because we have 2 free variables. So let's just copy this. Okay, and let's make it empty. And then let's make 2 of them. Okay, our free variables are in column 3 and column 5. So we have a trailing one in 3 and in 5. Everything to the right of the trailing one is 0, and everything below is also 0. Okay, so column 3, we have a 1 and a negative 3 that goes to the first vector as negative 1 and positive 3. Okay, column 5. Okay, so this is why these blanks are really important and the zeros are important. We have 1, 0, 1. So when we copy them over, change the signs, and that 0 goes into the second component. Negative 0 is still 0, and the other one goes here as negative 1. Okay, so that 0 counts as an entry. It goes over here. Okay, let's take some random dot products. Okay, every vector here must be orthogonal to every row on this matrix. Let's try the third row. Okay, is the third row orthogonal to each of these vectors? Negative 8 plus 3 is negative 5 plus 5, 0, 0, 0, nothing more. How about the second one? Negative 8, 0, 0, minus 5 is, plus 3 is negative 5, plus 5, that gives you 0. Okay, so of course, if we had more time, we could check that these 2 vectors are orthogonal to the other 4 vectors. You can do that. So our next job is to find another basis for W using this REF. And of course, since W is now the row space of this matrix, I hope you remember that the basis for the row space is simply the non-zero rows of the REF. So there's hardly any thinking involved, just cut and paste the 3 non-zero rows for our REF. It's hard to say that fast. REF. Okay, so there you go. And of course, W is still 3-dimensional. Remember that the number of vectors in any basis for a subspace must be exactly the same. Okay, so our last task is to express the 4th vector of S as a linear combination of these 3 basis vectors. Do we have enough space? Let's see. Yeah, we'll just sneak that in there. Okay, so that's our 4th vector. I want it as a linear combination of these 3 vectors. So let's put that here. Okay, and we will add them together, but we're going to need coefficients. Okay, and I hope you remember this as well. The this time they're leading ones are going to help us find the coefficients. Okay, we have a leading one in the first row, and everything below it is 0. We have a 3 in that column, so there should be a 3 as a coefficient there. Next, our next leading one is in column 2, so there's a 4 in the second entry. There should be a 4 there. Where is our next leading one? It's in column 4. 1, 2, 3, 4. So that should be a -5. Okay, do we get that vector? Let's ask. Whoops, I need to highlight the whole thing. There we go. So that is, boom, 3, 4, -9, -5, -2. Okay, so here are a couple of theorems that tell us nice properties of orthogonal complements, and we've already mentioned a couple of them. So the first property is that for any subspace W in Rn, the only vector in common to W and its orthogonal complement is the 0 vector. And we saw that in R2 and R3. We had two lines, they intersect only at the origin, and we had a plane and its normal line. Again, they intersect only at the origin. But this is true in general for any subspace of Rn. We already mentioned that the complement of the complement is the original space because W and W perp are complements of each other. So another way to say that is W and W perp form an orthogonal pair of subspaces. Now, here is another reason why the word complements is a good word for what's going on in what we just saw. In geometry, remember how when you study right triangles, you talk about complementary triangles. So, or complementary angles, I should say. So, two angles are complementary if they add up to 90 degrees. Like, for example, 30 and 60. So, in the right triangle, 30, 60, 90, 30 and 60 add up to 90. In the same way, if you have a subspace of Rn and its orthogonal complement W perp, their dimensions, the dimension of W and the dimension of W perp, add up to n. So, in a sense, they complete each other in Rn. So, there's a little more to this story than meets the eye. What we're going to find out later is that any vector in Rn can be uniquely decomposed as a vector sum. So if you have V, you can write it as W1 plus W2, where W1 is from your subspace and W2 is from its orthogonal complement. And we call this the orthogonal decomposition of V. So this is another good reason why they're called complements of each other, because they complete Rn. Any vector V in Rn can be written as just a vector from W and from W perp. Okay, so for our final segment, we are going to look at what is called the 2-for-1 theorem for bases. In this book, we are actually going to see several 2-for-1 theorems. So this is the first one of them. It says, suppose we have a subspace W of Rn, and we know the dimension of W is k. Of course, k is at most n. Suppose that W1 through Wk is any subset of k vectors from W. So we know the dimension, it's k, and we are given k vectors from W. Are we guaranteed that this is a basis? Of course not. B is a basis for W if and only if either B is linearly independent or B spans W. So I hope you're wondering, why is that an or? In the definition of a basis is supposed to be linearly independent and spans W. So yes, that word or is exactly the point, the magic of the 2-for-1 theorem. If you know the dimension of W is k, and you have k vectors in your hands, all you have to do to check if it's a basis is to check one of the properties that you're supposed to check, not both of them, just one of them. And of course, the easier condition to check is the condition of being linearly independent. All you need is the minimizing theorem. Now, the proof for this 2-for-1 theorem is, of course, in the book, so please read it. All right, so let's take a look at the last example that we did, where we had a subspace of R5, and here are, let's call them W1, W2, W3, W4, and W5. What did we do? We made the matrix of S, as usual, with these vectors in the columns of our matrix. We look for the REF to apply the minimizing theorem. The leading variables are in columns 1, 2, and 4, and that's why our basis vectors are W1, W2, and W4. Okay, we erased W3 and W5 because the minimizing theorem says that W3 and W5 are both linear combinations of W1, W2, and W4. So what are we going to do? We are going to ask, well, what if W3 really wants to be included in a matrix? In a basis for W? Is it possible that we can combine W3 with other vectors, also from S, to form a different basis? Okay, so I made these three sets of vectors. We know that the dimension of W is 3. So according to the 2-for-1 theorem, we need to have exactly 3 vectors in each set. And then we can decide, are you still a basis for W by checking whether they are linearly independent or not? We don't have to check spanning. All we have to do is check either spanning or linear independence, and the easier condition to check is linear independence, as we're about to see. Along those same lines, let's also say that if you have only 2 vectors, or if you have 4 vectors, too little or too many, automatically that cannot be a basis because your basis must have exactly 3 vectors. Okay, so how are we going to check for independence? As usual, we will have a test equation. But our test equation is usually for W3, W1, W3, and W4. But remember that any linear combination of these 3 vectors adds up to the 0 vector if and only if the corresponding columns in the REF, their linear combination, also adds up to the 0 vector. But these columns are a lot simpler. Here is W1. Column 1 of the REF. And here is column 3 for the REF. And here is column 4. Okay, so we want to make a linear combination x1 times column 1 plus x3 times column 3 plus x4 times column 4 must be all zeros. So let's just borrow this one here and turn that equal to 0. That linear combination will be 0 if and only if the linear combination involving column 1, column 3, and column 4 add up to 0. Remember that the solution to the original system, in this case it's a homogeneous system, is exactly the same as the solutions to the homogeneous system involving the REF. Okay, but look at all those 1s and 0s. All right, so the last 2 components are already 0, but in component 3, you already have 2 zeros. So therefore, x4 has to be 0. Okay, the only way that 1 is going to go away is if x4 is 0. Now you're down to 2 vectors. And let's work our way up. Oh, in the second component, that minus 5 has to go away. So x3 has to be 0. And now that these two are zeros, oh, that one has to go away. So x1 is 0. So we only have the trivial solution to our test equation. And therefore, these 3 vectors are linearly independent. Thus, they are a basis for W. Okay, so there's our conclusion. We only have the trivial solution to the test equation, and so our 3 vectors here are linearly independent. And by the 2-for-1 theorem, they also form a basis for W. So we're going to do the same thing to our 2 other sets of vectors. Hang on. Okay, so I put our second set up here closer to our REF. So we want to test W2, W4, and W5. So in our REF, here is the second column. So I need an x2 times column 2. Okay, and then I need an x4 times column 4. So column 4 is over here. And then I need an x5 times column 5, which is over here. Okay, so I want all of that to add up to the 0 vector. Okay, will we get only the trivial solution? So let's try to play the same game. These are already zeros, so we don't have to worry about them. But we have a 4 here. Oh, wait a minute, we have a 1 here. So that 4 is not all by itself. What about the next one? Oh, there's a 7 there. Ah, there's a 1 there, so it's not by itself either. First entry is all zeros. Fine. So we only have to worry about the second and the third components. Is there a way to make the 3 vectors add up to 0 without forcing the coefficients to be 0? Is there a way to cancel that 7 without using a 0? So what am I saying here? What if we just had a coefficient of 1? Can we make that 7 go away? I need a negative 7. And what about the 4? I need a negative 4. Okay, so that is a non-trivial linear combination that adds up to the 0 vector. So there is a non-trivial solution. So this set of vectors is dependent and therefore not a basis for W. The vectors are still from W, but they form a dependent set. So therefore, it can't be a basis for W. And as a matter of fact, let's go back to our REF here. We have column 5 over here. Didn't we see this in the minimizing theorem? Our column 5 is a free variable. It is a linear combination of our basis vectors, but in this case, the 7 and the 4 belong to x2 and x4, and our set really is 2, 4, and 5. Okay, so it's the same equation that we would get from the minimizing theorem. The 5th vector is 7 times the 2nd plus 4 times the 4th. And that is exactly the same equation, except the 2 vectors are put on the same side as the 5th column. If you solve for the 5th column, it's still 7 times the 1st plus 4 times the 2nd. In this case, of course, that means second column of the REF and the fourth column of the REF. Okay, our last candidate is the set with W3, W4, and W5. So let's make our test equation. X3, column 3, plus X4, column 4, and X5, column 5. Okay, and we add all of that. We want to get all zeros. Okay, so let's try our usual tricks. Those are all zeros already. There's a 4 here, but there's a 1 there. The 4 is not alone. 7 has a -5 here. 7 is not alone. Oh, but 3 is alone. So this time we have to look at the top. This time, x3 has to be 0. So once x3 is gone, now let's focus on just these two. Yeah, let's get rid of x3. Goodbye. Now we only have x4 and x5. Okay, now 7 is all alone. So therefore x5 is 0. And then finally, once x5 is gone, of course, that 1 is all by itself. x4 has to be 0. Okay, so what happened? We only have the trivial solution. There is only the trivial solution to the test equation. So our set is linearly independent, and therefore it is also a basis for W. Okay, so in our 3 candidates, only the first and the third are also basis for W. The second set was dependent and therefore not a basis for W. All right, we have reached the end of our video. Thank you so much for watching. As usual, you will find me on Facebook, and you will find the 4th edition at Facebook and at kendallhunt.com. So until next time, I hope you enjoy the rest of your day.